Everyone. I've just been checking out our Q&A stream and oh my goodness, there's just so much great stuff going on there. I can't wait to get back in and really dive around in there. We're up for our next presentation. We've got Mark Eaton, who is a Reader Services Librarian and Associate Professor at Kingsborough Community College at the City University of New York. Mark is committed advocate for code education for everyone. He believes that when librarians build open, appropriate and privacy-respecting technologies for their communities, it can be empowering for both librarians and their libraries. Mark's presenting on his Open Journal Matcher, a recommender tool for academics looking to find a suitable scholarly journal for their work. He's going to share insights gleaned while building the tool and discuss important questions around the ethics of algorithmic decision making. Thanks, Mark. Over to you.
Thank you. It's nice to be here. My name is Mark Eaton, as Bonnie said. I'm at Kingsborough Community College at the City University of New York. I do things at Kingsborough like work on our institutional repository and manage electronic resources. I've just started chairing our library's website committee, which is a big job because there's a lot of work to do there. But that's not what I want to talk about today. Today I want to talk about a project I built, which is a journal recommender tool. So what it does is you can enter an abstract and it will pick the journals that the open access journals that best match that text. So the goal is really to give people writing academic papers suggestions about where they can publish their work. And I'm totally not going to do a live demo because live demos are terrifying. But here's a screenshot and a URL if you want to try it. So you would plop your abstract in the text box and click search, and it will spin for a minute or two. And then it's going to give you some results for the top matching open access journals. And that's what it does. So I'm going to talk about how this works. I'm going to talk about some of the things I learned along the way. These are technical things, these are organizational things, these are ethical things, but I'm going to cover all of those. So you might want a tool like this if you're an academic writing an article and you want to find an appropriate journal for your work. In the past, when I did this, it was very time consuming because I would do it by hand. I would gather abstracts from a whole bunch of different journals over several years and read them all, and it would take me a couple days to go through this process, which is a lot of reading just to glean fit at a really high level. So I don't think this is necessarily the best use of my time, and I think that while reading for fit may be useful in some contexts, there's probably a better way to do this. There are other journal recommenders out there. This is not the only one. Here are some other organizations that have journal recommenders. These are probably all better resourced than my project, but mine fills a niche that I believe is not addressed by these other ones. It's fully interdisciplinary and it's fully openly licensed. So the code is openly licensed, it's MIT licensed, and the journals themselves are openly licensed. So it's on GitHub. You're welcome to fork it and run it yourself if you want, or send me pull requests. That would be amazing too. I would welcome contributions, of course. That would be phenomenal. This project is really inspired by the Directory of Open Access Journals API. The Directory of Open Access Journals API provides access to a lot of abstracts. And this was really exciting to me when I found out about it. The first thing I did was build a silly bot that kind of pretends it's a scholar and mashes up bits of abstracts. Anyways, not a good use of my time. But it did lead me to the Journal Matcher project. So you might be asking, like, well, what is in this directory of open access journals? That's a good question. There's lots of openly licensed scholarship there in many languages with metadata of varying quality. You could ask if the journals themselves are of high quality, and the Directory of Open Access Journals calls their content community curated, which doesn't sound super reliable to me, but they have put effort into cleaning up their journal list over time. So back in 2017, something like 5,000 journals were removed for not meeting standards. So I think as an author, you have to do your due diligence. You can't just assume that a journal is the best home for your work. You have to be careful about that and do your homework. So I started poking around the Directory of Open Access Journals website and API documentation, and I found a downloadable list of ISNs for journals in the directory. This was a spreadsheet. For those who don't know, ISSNs are unique identifiers for journals. They're sort of like ISBNs, which you might be more familiar with, which are unique identifiers for books. ISSN stands for International Standard Serial Number. And I could query the Directory of Open Access Journal API with ISSNs and get back lots of abstracts. So I could download these abstracts en masse from the API, and this allowed me to get like quite a collection of them. You have to be kind of courteous about this and not hammer the API with thousands of requests at once, but if you space it out a bit, you can get a good collection of abstracts to work with. So obviously this isn't the entire universe of scholarly journals, right? I ended up with maybe 6,000 English language journals, which limits the utility of the tool somewhat, but I think it's still enough data to make good recommendations. One of the problems I was actually facing was that I had too much data. So doing natural language processing on a dataset like this requires a fair bit of computing power, and I can't realistically process every single abstract in the directory in any feasible way. So I limited myself to the 100 most recent abstracts per journal, which is still a lot of data, but which was a trade-off for the sake of expediency, and it gave me a good corpus to work with. So these abstracts are in Google Cloud Storage, and I'm going to come back to them in a minute. To build the application, I use Flask, which is a Python web microframework, which is especially useful for building minimal Python web applications. It has more advanced features that you can plug in if you need them, but on its own, it's very basic and very flexible. And I run this Flask application on Python Anywhere, which is a service for running Python applications in the cloud. I don't think it's really meant for large-scale applications, but it was sufficient for my purposes. What I liked about it was that I could do most of my work in Python or in Bash, and I didn't need to worry about the web interface very much, and I didn't need to worry about an SDK or annoying interface like that to deal with. I could do my work in Python, which I was happy about. And the Flask application in this context does not do the data processing. It would be too computationally intensive to do all the data processing in the Flask application. So instead of that, the Flask application sends it out to a Google Cloud function. And a cloud function is also some Python code that I wrote, but it lives in the Google Cloud and it can be invoked with an HTTP request. So I invoke this cloud function once for each journal that's being compared. So the Flask application is making like 6,000 simultaneous calls to the Google Cloud function, which is possible thanks to asynchronous Python, which I'm totally not going into, but which was a key piece to making this work. So part of the story is that Google Cloud Functions can handle brief, intense spikes of usage like this, which was my use case, right? I needed a function that could be called many thousands of times at once, and maybe not again for hours after that. And this is one of the reasons why I use this approach. So here it is visually. I know diagrams like this can make your eyes bleed. I tried to make it as straightforward as possible. I'm gonna explain this really, really quickly. The user at the top left inputs their draft abstract. It gets validated for being an appropriate number of characters, like not too long or anything. It checks to make sure it's in English. It calls this cloud function about 6,000 times. I've shown about 7 of them there. The cloud function draws upon the abstracts which are in Google Cloud Storage, close at hand, and it does the comparisons, and it returns a calculated similarity score back to the Flask application. So the Flask application gathers all these scores, sorts them, and does a couple more API calls to get the titles of the top matching journals, and then returns those to the user. So let's talk about how this works under the hood. I don't have a computer science background, so when I talk about algorithms, there are points when I run up against the limits of my understanding. And for those of you who know more about these things than I do, please forgive my attempts to inadequately deal with complex topics. I'm going to do my best at those moments where I'm at the limits of my understanding to point to others' work that's more knowledgeable than mine. But with that being said, let's talk about how it works under the hood. I'm not going to bore you with my initial sort of naive attempts at solving this problem. It turns out that processing many, many thousands of abstracts in a very short time is not a trivial challenge, and I learned some lessons while doing this. After some false starts, I settled on Spacey, which is a natural language processing library in Python that has a lot of useful models and abstractions built in. It is also helpfully MIT licensed, which is great. My early pre-Spacey attempts would not even run to completion. So when I found Spacey and I could actually make it through 6,000 journals of abstracts without crashing my computer, I was very happy. That was a good early victory. And as a bonus, it produces decent recommendations. I was happy with the journals that were being surfaced for the most part. We can talk about that in a second. So Spacey has built-in tools that can extract meaning from a text blob, which is kind of what I wanted to do here. It does a bunch of other things too that I'm not going to touch upon. But one of the things it does is it can evaluate text using word vectors. And you might be like, well, what are word vectors? This is one of those points where I'm at the limits of my understanding, so please bear with me. This tutorial that's linked here by Alison Parrish is super useful. She does an excellent job explaining word vectors, and the examples that are in the following slides are drawn directly from her tutorial. So I'm going to follow her lead and explain word vectors using animal vectors as an analogy, and you'll see what I mean in a second. I'm going to consider the features of animals much in the same way that Spacey considers the features of words. So bear with me while I go down this rabbit hole. Here are some animals ranked by cuteness. This may seem kind of arbitrary. It is kind of arbitrary. These are rankings by Alison Parrish. She came up with this scale of 1 to 100 for ranking the cuteness of animals. And that's like a way you could describe animals, right? Like it's a thing you could do. You could describe them in that way, and you've captured something about them with that score you've given them. For context, there's my dog. She is a cuteness reference point. She's in the other room where she's not bothering me right now. But you could also rank animals by size, right? Like this is another way you could rank animals. They're not all the same size. Some are bigger, some are smaller. You've now described these animals in two different ways, two different dimensions. And you could plot that on a two-dimensional chart, right? Where size is one axis and cuteness is the other axis. And you can see where these animals are in that two-dimensional space, and you can kind of see which ones are near each other in a way that you really couldn't with the table on the previous slide. So that's kind of interesting, right? And you could imagine a third dimension to this chart, like fluffiness too. You could chart it with size and cuteness and fluffiness as the three axes. And that's kind of easy to imagine in your head, but harder to show on a slide in a slide deck. You could also do this with like 4 dimensions or 5 dimensions or hundreds of dimensions. And that's probably impossible for us to imagine as humans spatially, but a computer can do that really well and can capture data across about these animals across many, many different criteria. And my point about this is that Spacey has done this with words. So it's created models where words are vectorized using up to 300 dimensions. So you're capturing meaning about these words across 300 dimensions, which is kind of mind-blowing, but it's neat that these models exist. And you can apply these word vectorization models to text and save it as a variable, for example. Then you can compare these vectorized objects really easily because Spacey vectorized objects have a built-in similarity method that allows you to compare two objects. So it'll spit out a score on a scale of 0 to 1, where 0 is like these texts are not at all the same, and 1 is these texts are identical, or anywhere in between. And it makes it easy to compare the similarity of one blob of text to another. So you can loop through a list of journals like this and compare them to the draft abstract one at a time to get similarity scores. It's time-consuming, but it's actually plausible. So the positives and negatives of this approach. One positive is that it works. That was a big win in this project. It might surface journals that you hadn't considered, which is really the goal. The goal is not only to be relevant, but also to be serendipitous. So it covers all disciplines because it's drawing on the directory of open access journals, and it's fully openly licensed. The downside of this is that, like I said before, it's not really guaranteeing journal quality. The data set isn't complete. There are journals that aren't in here because they aren't openly licensed. There are others that aren't in here because they don't have complete metadata. There are others that aren't in here because they aren't in English, and my recommender only knows how to score English language abstracts. Lastly, it's a bit slow, but I think it's in an okay place right now. I'm not going to worry about the speed too much because speeding it up requires compromises, and I think that it's not necessarily a win to speed it up. So the next couple slides I think are the most important of the deck. We need to be thinking critically about algorithms and how they work. I'm leaning on Spacey's word vectorization and matching algorithm, so in a sense I'm trusting it, and partly I'm willing to do this because it gives what appear to be intuitively good results. And this may be good enough for a work in progress, but in another sense this is not good enough. There are ethical blind spots in this approach. These are the result of my relative position of privilege. These are the result of my limited understanding of the Spacey internals. These are the result of me working on this project by myself. So none of us are ethically perfect. We all make ethical mistakes. I'm no exception, and ethical decision-making works better with multiple voices and diverse voices. So here's a bibliography to think about these questions. I recommend all of these. They're excellent. If you have more to add to this list, I would certainly be very glad to hear from you. So I would argue that the journal recommender is ethically incomplete at this point. And I think that's okay. And the reason I say that is because I don't think we can really aspire to an ethic that does not require revision. And really crucially, I think that ethical incompleteness is an argument for building open systems. Open systems are revisable by anyone, so they can be improved not only technically, but ethically. And when we equip more people with the capacity to reach in and work with the tools, we broaden the ethical foundations of the project. So this is worth thinking about in the context of our GLAM organizations, because in our GLAM workplaces, we often cede technical decision-making to a small number of technologists. These are people who usually work directly with the tools. Or we allow them to translate their technical decisions for the rest of us. But I would argue that this is not the best model. Concentrating the ethics of technical decision-making in the hands of a few people is really not a good idea. And with open systems, it doesn't have to be this way. We can encourage everyone in our organizations to engage with open tools as much as they want, as much as their comfort level and their interest level and their available time allow. So instead of having translation by only a few technologists, we can have more people reaching in as much as they want. And when we reach into our technologies, we can bring back knowledge to share. There's no danger of running out of technical problems to solve. There will always be more. That's kind of a given. So where this project goes from here, there's a few things I'd like to add to it. I think multilingual support would be really clutch. There's clearly demand for this because the journal matcher gets a lot of non-English language requests. The problem I'm facing here is that the directory of open access journals skews heavily towards English language publications by like an order of magnitude. So I'm going to try to implement multilingual support, and we'll see how it goes. I need to make some automated maintenance of a lot of the background work that goes into this tool because it's boring and it could be automated, but I'm not going to talk about that. Lastly, I'm waiting to hear about funding for this project from my university's research foundation. I'm hoping that this can spur further work on this project because development is not free, and hopefully I can get something going there. So I learned a lot about automated matching. I think you need to take a tool like this with a grain of salt, is my conclusion. Tools like this can make good recommendations that may be both good and unexpected, which is really the goal. But there are trade-offs in building a tool like this. So you can't really have everything you want in a matcher tool. Those other tools that I showed earlier, I guarantee that they also have compromises and trade-offs that they made while they were, the builders made while they were making them. I've done my best to make what I think is a useful tool. So lastly, I want to say thank you. I think there's value in librarians and GLAM professionals writing code. We're positioned at the confluence of a lot of information tools, and there are valuable opportunities for us to contribute here. So we can really build the open source information landscape we want to see, and we can broaden the perceptions of what a GLAM organization can do. And that's it. Thank you.
Wow, Mark, thank you so much. I can already hear the excited liaison librarians just, minds exploding with what you've brought here. But I think too, those issues around the ethics and positioning our own privilege are incredibly important. And I can see in the chat that people have been really discussing that. So what I'm going to do is let you jump off. So Mark is going to jump into our Q&A stream. So we'll have 10 minutes there, and then we'll bring you all back in for our next speaker, Hugh Rundle, who will be presenting at 12:10. Thanks again, Mark, and we'll see you in the Q&A.